Levenson, the Executive Director of the Passive House Network. And it's good to be here with you in the special PHN Presents with Enrico Vonalari from Emu and their new report on energy standards. And particularly, we're focusing today on the California results, but I think we're going to be also looking at the bigger report as well. So I'm glad to introduce Enrico, the author of these reports. He is a co-founder of Emu Passive. He's an established expert in the International Passive House Construction Standard. He's known for being able to see complicated, cutting-edge data through the lens of practical on-site implementation. He has extensive work experience in Australia, Europe, and North America, with a specialty in building envelope design and analysis. He is the author of the Emu North America Certified Passive House Tradesperson Training Textbook and the lead trainer for Emu's Certified Tradesperson courses since 2017. Look out for upcoming CPHT courses in places from Santa Barbara to Oakland to Denver, New York City, Boston, and many more cities across the US in 2024.
Hello, everyone. Ken introduced me very nicely. I'm the co-founder of Emu Passive. We used to be an architectural practice back home in Italy. And when we moved to the US in 2016, 2017, we switched gears and we focused on education and moved away from design. The reason we did that was because we saw in education a better way to for mass adoption of passive house by the mainstream market. And as part of our research for our curriculum, we found we had the need to compare passive house to other building standards that are available in the US, because builders, architects, other people that will come and take our training would ask us, how does passive house compare to Energy Star or the IECC code, or in this case, the California Title 24? So about 2.5 years ago, I started fiddling with Excel, and the purpose of that was to create a short post to go on social media, and that post kept on growing. Never got published as a post on social media, but it actually became a very large report. Today, we go over the results for California. Let me see if I can start. There you go. But that is part of the larger research that we did, as Ken said. So today's learning objectives, especially for those that are pursuing AIA, continued education credits, are outlining the performance standards under considerations for this report. This is where we today present specifically the results for California, describe key performance indicators that were included in the report and why we selected those indicators. We're going to outline the results of the report, comparing different building standards for these reports, as well as we're going to describe the key factors that drove these results and how professionals can utilize this data in designing better buildings, and also inform their colleagues and their clients about passive house and the reason why it's so important to build better buildings. So I divided this presentation into two parts. One is the overview of the actual full report, because this gives the context of how these California results were developed. And then in the second part, we're going to talk about specifically what this means for California. So taking a step back and looking at the Emu report on building standards, we are in a market where there's a big push in North America to drive towards electrification, and that is driven by the top also, with the Biden administration pushing for 80% renewable energy production by 2030, 1 every 3 vehicles sold by 2030 to be electric, and to quadruple the use of heat pumps in residential projects. So there's a big push towards electrification. This is in the context of also trying to make our buildings better. In fact, a quote that I always love to bring up by Rand Koolhaas is that we people are voluntary prisoners of the buildings that we build. So we build our own caves, and we spend a lot of time in fact, we spend over 90% of our time inside buildings. And so the quality of the buildings that we occupy has a direct, strong impact on our health and well-being. And that is never underestimated. So in comparing these standards, we had a strong focus on the quality of the building, not just in terms of energy performance, but also on how these buildings can be good shelters for people. Now, a question that we always ask to builders and people that participate in our training is, in average, how many years do you think an American family stays in a house before they move out again? This is key because all the investment that we make for our buildings impacts people that occupy the building. And the answer that we get from builders and from professionals in the US is typically 5 to 7 years. And that is inaccurate, that is grossly inaccurate. That is actually 13 years in average. And this is not a statistic coming from PHI or from the Passive House community. This comes from the National Association of Home Builders. They could care less about building better because they have their own interests. But this is independent data that shows how long people stay in buildings, even in the US. And that is very important to keep in mind throughout this presentation. These are the standards that we considered for the whole report. The next few slides, I'm just going to brush over quickly to give you the idea of what's going on. These are the 50 projects that we selected for the study. These come from our own pool of projects that we work on for the consulting side of Emu. Emu is basically split 50-50 training and consulting. And we selected this project to be consistent. In fact, we tried to have a blend of different climate zones so that one climate zone would not overly impact the results. These are all single-family homes, new construction projects, as a way to have a high enough number of projects to be statistically relevant, but also to have a pool of projects that is fairly consistent so that we can have a more consistent set of results. The split between climate zones was a quarter of projects were selected in climate zone 2 and 3. A lot of them were in California. As many were in colder climate zones, and then half of the project total was from mild climate zone. These refer to the national climate zone definition. These are actual projects. These are not some random standard design that you can find in some abstract ASHRAE standard. These are actual design. There's a client, there's a site, there's a surrounding, there's an architectural design. And the high enough number of projects allows us to dilute those aspects that would be outliers. For example, a lot of glass, a lot of high form factor. If you download the report, there's going to be a link towards the end of the presentation. You can find all the data for these projects. Don't want to spend too much time on this right now. There's a range from 500 square feet to about 5,000 square feet. We tried to select a range that was consistent. And then this is put in the context of the form factor. Don't need to speak too much about that today. But again, please look at the main report to have more data on that. The analysis tool, we modeled all of these projects in Design PH and PHPP. We did that out of convenience because we had those models already set up in our consulting practice, and the format makes it easier to elaborate. We did not want this study to become a study comparing two or three or more different softwares. We want to compare the requirements of different building standards. We're going to get to that. And in fact, the energy performance is just a part of this result. In fact, it's not even half of the results. So I'm going to skip over this. We're going to see a little bit more in the next few slides. The assumptions, buildings were all electric because that is the direction that the market is going. All buildings have active heating and cooling via heat pump, including ones in the mountains in Colorado. Domestic hot water via heat pump water heaters. interior temperature set at 70 degrees for wintertime and 74 degrees for summertime. That is something that we decided for the assumption because it's more representative, in my opinion, for the way buildings are operated at in the US. So when we talk about PHI and fuse requirements, we're going to come back to that. All buildings have continuous pressure ventilation, which is a big it's a stretch for code minimum building. We talk more about that in the main report. All standards were modeled to the minimum level allowed by that standard. So if Title 24 or Fuse or PHI or Energy Star, whatever, have a minimum requirement, that is how we set it up in the model. Talked about effective R value set up in PHPP. We did not account for the impact of catastrophic thermal bridges. And that is something that we're going to talk about in terms of prevention of mold condensation and how Title 24, for example, does not address. But that was not included in terms of the impact on the energy performance. So again, coefficients, shading was included, and I'm gonna skip on this. You can find more on this in the main report, but this should give you an idea about how the study was conducted. Now, comparison metrics, we looked at thermal comfort, indoor air quality, resilience and durability, operational energy efficiency, and embodied carbon. So we looked, these are the main metrics that we included in the report. So the energy efficiency is only 1 of 5. We're going to look at, going to the list when it comes to California, talking about indoor quality, comfort. So the energy performance is only one piece of the puzzle. The report has a big summary table that is kind of difficult to navigate. By the way, at the end of this slide deck, there is a link to a channel on our YouTube platform where we have recorded videos to cover these individual topics if you want to learn more. Reduction of site energy for heat and cooling. Again, this is the data from the main report. We're just about to switch to California specific results. In average, this is what you can expect. For the main report, we use the 2018 IECC standard as the baseline. And you see that if you don't account for PVs, California Title 24 does not look super performing in this context. Does not look very good at all. We're going to come back to this point, but fundamentally, California Title 24 is very close to the requirements to the 2018 IECC, except for the need for heat pumps and PVs. We're going to see how that impacts the resiliency of the building. This is benchmarking the same results for IECC and PHI. Again, look at the report if you have more information. This is for the whole study, so don't want to spend too much time on this today. For the EUI, something that we covered in the report and we're going to touch base on for California today is that once we start factoring in the adoption of electric vehicles, then the efficiency of building envelope becomes crucial for our infrastructure. So in this graph, you see the solid gray is the EUI average for the buildings that we consider in the whole study. For heating, cooling, domestic hot water, and other appliances. And then the dash gray and white is the additional energy use intensity EUI that we have once we start charging vehicles at home. The dash black and white here on the right-hand side shows 2 electric vehicles per home charged. What is interesting is that today you can build a code minimum building, a building that complies with the IECC standard. And for the same amount of energy consumption, you can build a PHI passive house and charge 2 electric vehicles. So in this context, for our infrastructure, it's key to have infrastructure, the electrical infrastructure. If we don't want to double the number of power plants that we have, we want and need to invest in the quality of building envelopes so that we can minimize the impact that buildings have and the need for energy that buildings have, so that we can free up some power to charge electric vehicles. Again, this information is described more in detail in the main report. Please refer to that to have more detail. Because the results are very complex, we talk about comfort, we talk about indoor air quality, we talk about resiliency, energy performance, and embodied carbon. It's difficult to add 1,000 kilowatt hours to 3 ACH50 to a filtration grade of a filter. So because of that, for the report, we developed a scoring system where for each category of these 5 listed here, thermal comfort, indoor air quality, resilience and durability, operational energy reduction, and embodied carbon, we gave points to each standard, and we had a final grading of each standard. This is, again, illustrated better in the main report, but it's a way to kind of have a more simple way to communicate the value that each building standard brings to the table. Now, coming to the result for California, we have 11 projects that we did consulting on, mostly around LA, Bay Area, and some in the mountains too. So we have a breakdown like this for California climate zones. It does not represent all climate zones. It does not represent all climate zones the same way, but it's a fair spread, in my opinion. It gives us a good sense of what's going on in this state. So for California 2024, we derived the requirements to then be modeled in PHPP from the California 2024 requirements. And this was our baseline for this appendix. Then for the FUSE standard, we used the 2015 FUSE Plus mostly for reference. We did not really model it because it's 2015, so it's what, 7 or 8 years old. We used the 2018 FUSE Plus core, and we used the 2021 FUSE Plus core as well as the 2021 FUSE Plus core prescriptive. These are standards that we used in the modeling for this report. The FUSE prescriptive requirements for the 2021 FUSE Plus core prescriptive we derived from FUSE website, project by project, as well as this is for the prescriptive FUSE, and the performance-based FUSE, the 2018 and 2021, we use the online calculators to determine the project-specific targets for heating demand and cooling demand. Now, remember, this whole study is set up to have 70 degrees interior temperature during heating season and 74 during the cooling season. FUSE and PHI both use 68 degrees for wintertime and 77 for the summertime. So the way we did it was we determined the maximum allowed heating demand for FUSE to the website. We set up the PHPP models to meet that, assuming 68 and 77 degrees set point temperatures. And then we upped those temperatures to 70 and 74 to get the heating and cooling demand results. Same we did with PHI. For the International Passive House Institute, we modeled both the PHI passive house and the PHI low energy building. And in the same way, we set up the PHP models to have 68 and 77 set point temperatures, and then we changed those to be 70 to 74, as that was deemed to be more realistic for the way buildings are operated in the US. Starting off with the metrics for building quality, as we call them in this report, we covered thermal comfort, indoor air quality, durability, and resilience. Starting with thermal comfort, the comfort criterion addresses the radiant asymmetry or lack thereof, and the absence of downdrafts. And the air tightness, which is the second parameter that we included in the thermal comfort bucket, addresses drafts and stratification or prevents them. So for passive building standards, which include PHI and FUSE, they have similar comfort criterion requirements as well as air tightness requirements. We're going to see those in detail for California. Whereas other building standards, in this case, Title 24, has no requirement for air tightness. We're going to see more of that later, as well as it does not have any requirements for thermal comfort in terms of specifying window requirement. This is the U values or U factors required by each standard. On the left-hand side, we have the uninstalled parameters. Uninstall means that it's just the value that you get from the window manufacturer, whereas on the right-hand side, you have the installed whole window U values. And that is because PHI's requirements are driven by the setting goals for thermal comfort. And so using the installed also factors in the thermal bridge of installation. And these specifically are the columns, not that we care too much about individual data here. Looking at this closer, we assume 0.04 watts per meter Kelvin installation PSI values for all projects and for all standards. And to be honest, that is pretty generous with regard to California Title 24, because if you have a traditional nail flange installed, the PSI value there can be twice as high or 3 times as high, especially if you're using some aluminum nail flange. So that using a 0.04 is very generous with regards to California Title 24. The U values installed were calculated for PHPP and averaged out. With these results from the table on the right-hand side, California Title 24 fails to deliver thermal comfort in about every other project. Let it sink in. It's California, it's mild. I'm from Italy, and everybody thinks that Italy is a warm, fuzzy country, but it's actually, it can be very uncomfortable. I also lived in Australia, in Sydney, Australia, for a couple of years, and that was the most miserable winter I've ever spent. I lived in Germany too, I live in Colorado, but because the assumption was that Australia is warm, then buildings were built very poorly, and there was no requirements for thermal comfort. So the current requirements for Title 24 for windows lead to half these projects fail the comfort requirement. For half of these projects, FUSE requirements are actually less stringent than Title 24. So that is something that when we were comparing some FUSE prescriptive requirements to the Title 24 requirements for Windows, in about half the projects, the requirements for FUSE were less stringent than Title 24. And PHI's requirements achieve the higher level of comfort. This is the average temperature that you get on the interior surface of windows and doors by project and by building standard we consider. And the orange dashed line is the threshold for thermal comfort. If you're above the line, it's comfortable. If you're below the line, it's uncomfortable. And you see that, you know, California, yes, it is milder than the rest of the country, but there are conditions and there are projects that we consider here that are really failing. Some of them are close, some of them are above the line, but some of them are very failing because just like in the IECC, thermal comfort is not really a main driver of these parameters and requirements for windows. Indoor air quality, we are going to talk about fresh air supply, fresh air filtration, air tightness, and avoidance of mold and condensation, as well as other indoor air quality goals. Ventilation rates by building standards. California Title 24 follows the ASHRAE 62.2. FUSE has its own requirement, which is a maximum between supply and extraction. PHI has its own requirement between supply, extraction, and volumetric. 62.2, this is where we're talking about building standards. We're not talking about individual projects. ASTRA 62.2 assumes the number of occupants to be the number of bedrooms plus one, and Fuse, on the other hand, assumes the number of occupants to be the same as the number of bedrooms. And I had conversations with a few people about this. They were pushing back on this parameter, saying that Fuse follows the same ASTRA 62.2. It's not true. If you look at the Fuse guidebook version 3.1, I think it's page 35 or something, it clearly states that the number of bedrooms is the number of occupants. And in this study, we used the actual airflow rates that we, EMU, specified for the project that we were working on for PHI. So this is the big table showing the airflow rates, looking at what that means in terms of indoor air quality. Standard EN 13,799 assess the level of indoor air quality were calculated on the CO2 concentration levels. Air filtration is not accounted for, air tightness is not accounted for, it only looks at the CO2 levels, but it's a start. We're going to see the other parameters later in this presentation. This is the airflow rates for all of the standards we consider for the whole report, and this is for the averages across all projects for California. And you see that the three standards we're looking at, Title 24, Fuse, and PHI, all fall within the high indoor air quality on the CO2 concentration levels. Now, airflow rate is not the only part of it. This is where we start talking about exterior pollution. This is a picture of downtown LA. And this map shows the daily average concentration of airborne solid pollutions, particulate matter 2.5. And you see California looks pretty bad, as it does part of the Midwest around Chicago. And we care about particulate matter 2.5 because it causes cancer. So that is why we care. This table comes from the main report. It shows the filtration grade required by each building standard in terms of MERV rating, and the filtration grade that each standard requires. The part that we care about, the particulate matter 2.5, is falls within the column 1 to 3 microns, which is highlighted by the orange box. California Title 24 requires MERV 13, which is very good. Because it filters out over 85% of particulate matter 2.5. Fuse has a more relaxed requirement, MERV 8, which only filters out about 20% of particulate matter 2.5. And PHI is the same as California, MERV 13 requirement for air filtration. On the same line, we want to protect our environment from other types of pollution, including wildfire smoke. This is a study from Cameron Monroe down in Melbourne, Australia. They actually monitored airtight buildings alongside conventional buildings during a big wildfire smoke a couple of years ago. They call it bushfire smoke, but it's the same thing. And this graph shows the concentration of particulate matter 2.5 in a standard home, which is the red line, which is consistently higher than the concentration you have in an airtight building, which is the green and yellow lines in the same study. Now, this is Cameron Monroe's own house, and he retrofitted it down to about 1.2 ACH 50. So it's not really to the level of 0.6 passive hours or 1 for an NFIT, but it's still significantly more airtight than the 15 ACH 50 of the conventional home. And so you see that consistently, the building that is more airtight keeps the occupants more protected from exterior wildfire smoke, which in this graph is shown by the blue line going up and down. This is 3 or 4 consecutive days. Now, in Colorado, we had a big fire, the Marshall Fire. And on the Passive House Accelerator, you can find an interview with Mark Attard. Mark Attard is a colleague here in Colorado, and he spent a lot of time air sealing his existing building. And so while a lot of his neighbors had the homes damaged by smoke, his house was much more airtight, so he was able to move back in very quickly after the fire was out. So airtightness is a significant factor in having indoor air quality inside buildings. And California Title 24 does zero towards the airtightness of the building. So in my opinion, the approach that Title 24 has put in place, it's half done. We have the ventilation, we have the filtration, and we have nothing with regards to the airtightness. So that is something that I think needs to be addressed in the near future. This is a summary of the result that we covered so far. The ACH values and Q50 values that we list here are the median values across all 50 projects of Emu's report. The ACH 50 value is the volume-related maximum allowed air leakage by building standard. Fuse does not set actual ACH 50 values, but we have calculated those. I think it comes up later in this presentation. It averages out at about 1.1 ACH 50 for the Fuse core and 0.9 ACH 50 for the core prescriptive. California 3024 has no actual maximum allowed. There's no need for testing, and the building can be as leaky. I think the page on 3024 is like 3 lines that tells you air seal everything, and that's it, which is kind of, I was very shocked and disappointed when I read that in reviewing Title 24. Fuse prescriptive is actually more stringent than the Fuse performance-based. And then PHI passive house requirements require the building to be about twice as airtight as a Fuse performance-based. And then we talked about the filtration, something about the efficiency of the fans. Title 24 sets a maximum of 1 watt per CFM consumption for the fans for the ventilation system. It's about 0.83 for Fuse and about 0.757 for PHI, in case you were wondering. Avoidance of mold and condensation is one of the most misunderstood part of passive house. Everybody and their dog knows about the prevention of interstitial condensation. All 12 building standards that we have considered in the main report address it, and that is addressing interstitial dew point, which is different than, it's a different phenomenon than surface mold and condensation, which is when we have thermal bridges, and thermal bridges cause lower localized temperature that provide the ground for mold to develop. And mold requires no condensation. And that is something that most American professionals still have a very hard time to grasp, because it's so not addressed by code that is, sounds very new. This picture on the right-hand side shows the after the fact of a building retrofit where they only changed the windows because code allowed that. The building became more airtight and filled up with mold because it had no actual ventilation system. So this is something that the more we try to air seal our building, the more we try to make our buildings more energy efficient, the more we need to care, because in my opinion, there's no point in making a building more energy efficient if it is also not healthier. Fuse addressed this partially. They accept the NFRC condensation resistance and the condensation index, as well as the AMA condensation, something, whatever it's called, and those are not actual ways to address condensation and mold because it's a blend of different metrics. I'm happy to answer more questions on this later. PHI does require this. This is one of the hard requirements of PHI certification, called the hygiene criterion. Hygiene equals absence of mold. And what it looks like is basically thermal bridge modeling, where you can see localized lower temperature on the surface. In this case, we have a 3D thermal bridge of a beam crossing over to the exterior, uninterrupted, non-thermally broken, which causes all kinds of issues, mold and condensation. And this is by an architect that is famous to be a green building architect, but has never built a passive house because he wants to pull off this stuff. Other building goals for air quality, Fuse requires the EPA Indoor Air Plus certification, which has some requirement. It's a checklist. It's not, there's nothing too fancy about that. There's moisture control, radon, pest control, HVAC system requirements, combustion pollutants, and other materials in terms of limiting VOC and other parameters. I did not have time during the study to investigate how much good this certification does to an actual project. I'm considering pursuing this for my own house to be built in a couple of years, just as a way to like try to improve the quality and also having a better experience with this standard. As I mentioned, DOE, Zero Energy Ready, and Fuse required this certification, which was accounted for in the scoring that I mentioned earlier. Talking about resiliency and durability, we talked about the reduction of air leakage because it makes more durable. We're going to see about that. Abundance of interstitial condensation, abundance of mold and surface condensation, thermal resilience. The air leakage reduction, this is where we look at a bit more in detail. PHI requires the volume-specific requirements, so the ACH50. The surface area specific requirement, the Q50, is required by Fuse, with a note that the prescriptive Fuse has more stringent requirements than the performance-based, and PHI for very large buildings has a surface area specific additional requirement for certification. And then there is California Title 24 that has no requirements. The value that we see in the next slide of 4 ACH50 for California Title 24 is what we used in the modeling, because we cannot use infinite in PHPP, but it was derived by how the software is set up for California Title 24. There's no requirement for California Title 24. It can be as sleek as you want it to be. Volume-related ACH50, we calculated, you cannot convert 0.6 ACH50 to Q50 in general. You can do that for a single project because it has a combination of net volume and envelope area. But because we chose 50 projects to do this intentionally so that we could have a high enough number to draw some statistical conclusions. And so for Fuse does not have any ACH50 requirements, but we were able to calculate those from these 50 projects. This is the requirements for Title 24. As I said, 4.4 is not the actual requirement, it's just what is in the software. Fuse requirements for smaller buildings, it can allow up to 1.9 ACH50 based on the same 0.06 CFM per square foot requirement for the surface related. And then this is for PHI on the right-hand side. This is what it looks like, but we can skip that. For the Q50, surface related, same way PHI does not have any Q50 requirements, surface related requirements for this size of buildings. So we calculated these backward from the volume and envelope area of these projects. This is again, California, Fuse, and this is basically looking at the same air leakage measured at the blower door test and then related to the building volume or the building surface area. These are the median values across all 50 projects. On the left-hand side, we have the volumetric, and on the right-hand side, we have the surface-related values. required by each standard. You see that in average, Type 24 is through the roof, literally. Then there's a fair amount of building standards that require about 1 ACH50. Fuse performance-based is about 1.1 ACH50. Median values across the 50 projects that we modeled, and about 0.9 ACH50 for the prescriptive fuse. Whereas PHI low energy building is 1 ACH50 and 0.6 for PHI passive house. Now, the ACH50 is more commonly known in the US. It is harder to meet for small buildings, and it is not as indicative in very large buildings. The Q50 value, the surface area related metric, is less common in the US. It's more strict on large buildings. It's more lenient with regards to small buildings. It's also more lenient on what I wrote here, poorly designed buildings, or rather buildings with high form factors, because the allowed air leakage is proportional to the amount of surface area that you have. And so the higher the form factor, the more inefficient your building is. Also, the higher the allowance you get for the blower door test using the surface related metric. This is talking about the metric themselves, because that is an actual impact on evaluating them. And for California Type 24, it actually allows infinite air leakage because there's no requirement at this point. Talking about resiliency, this is the Icebox Challenge in Denver, Colorado for the conference. I'm going to speed up a little bit. These are the pods that we have in class for the workshop where builders build mini passive houses. They both mimic the resiliency of a passive house, where the envelope is very well insulated, very airtight, and so it can keep the heat in case of the pods over time, even if the power goes out, and it can keep the cool in case of the Icebox Challenge, even when the air conditioning goes out. This is very important for California, because when the grid fails, then the building is able to remain livable, even if the heating and cooling system are not running all the time. Now, to try to mimic that, so this is kind of the thermos versus coffee pod functioning that we have. To try and address that, we looked at the heating and cooling loads, and we tried to extrapolate the inclusive R value for each building standard to kind of estimate which building standard make buildings more resilient. This is the formula. It's described better in the report. I'm trying to speed up a little bit because we are falling a little bit behind. The most resilient standard that we have considered is PHI passive house. You see that in this scenario, the California Type 24 does not look that well. It's going to look better when we talk about energy efficiency, but that is thanks to the heat pump requirements and PVs. In other words, if or when those fail, the envelope of a California Type 24 building is not very good. And that leads to building become unlivable much quicker. Now we start talking about energy and embodied carbon. We are going to look a little bit of our site findings, site energy for heating and cooling, energy use intensity, and future proofing for EV adoption. For heating and cooling, this chart shows the 11 projects we looked at for California, modeled for California Type 24 in brown and PHI passive house in yellow. These two graphs show the need for heating on the left-hand side and the need for cooling on the right-hand side. And yet again, this is where the data is here to educate us about priorities, because you may think that California is hot, and so who cares about the heating part? This is something that I've seen over and over back home in Italy, where people believe it's a hot climate, and it's actually it's a heating-dominated climate for the most part. this graph here are site energy. And so in this, we factor in that when we switch to heat pumps are much better at producing cooling, much more efficient than they are at producing heating. So when we factor in this difference in performance, then the reduction of heating becomes a priority, even in mild climate zones like California. Then something about net zero as we go towards looking at EUIs and electric vehicles is that one of the first definitions of net zero building was given by the DOE back in 2015, and it did not include on-site charging of cars, only on-site charging of vehicles that were used within the site. Whereas the newer building standards for net zero carbon and net zero energy do include on-site charging of electric vehicles. So the market is moving forward, and the net zero is evolving to start including charging of electric vehicles. And we're going to see how difficult it's going to be net zero if the building is not passive house, even in California. Skipping a little bit forward, the heating and cooling demand, this we calculated for each project and building standard in PHPP. And this demand is only driven by the efficiency of the building envelope. We don't factor in the heat pump system here yet. We assumed heating and cooling via heat pumps per the California Title 24 minimum compliance, and the efficiencies or losses due to distribution, emission, regulation were disregarded in the study, just to simplify things a little bit. And at this stage, when we look at site energy, the production of PVs is not accounted for yet. This is what all 50 projects look like, and this is what the California project look like. Overall, the average site energy for heating and cooling looks like this, with reduction compared to the Title 24 of about 25% for the fuse prescriptive, 46% for the 2018 fuse, about 43, so a little bit less performing for the 2021 fuse core. That's because they raised the allowance for heating and cooling in the 2021 update, and then about 33% for PHI low energy building, and about 55% reduction in site energy heating and cooling for PHI passive house. Now, for domestic hot water, PVs, and other appliances, this was not really the focus of the study. The study was focused on the quality of the building envelope, because that is where a lot of value is for occupants. That's why we spend so much time talking about comfort, indoor quality, and durability. We assume 750 kilowatt hour per person a year for domestic hot water via the heat pump water heater. And we looked at PV system size by the requirements of California Title 24. This is the breakdown, and this is the site EUIs for the different standards in average for the California project, not including yet charging an electric vehicle on site. When we start doing that, this is what it looks like. This is the same graph we saw earlier in this presentation, where the solid gray is the site energy for heating, cooling, domestic hot water, and other appliances. And then the dashed white and gray is, in this case, charging one electric vehicle. So you see that even in California, reducing the need for heating and cooling by adopting passive house can free up bandwidth in the electrical grid to support charging of electric vehicles as they become more and more widely adopted. So, and this is my recommendation, is to look at performance-based standards, because that is the only way, in my opinion, that you can optimize the way the building performs and make informed trade-off. Now, for the sizing of PV system, this is something that is already included in California Title 24. These circles show the size in output, so kW, as well as square feet of PV system needed to balance out for net zero the buildings that we have included in this project. In the case of no EV charging, that is the smaller light gray circles at the bottom, and in the case of charging 2 electric vehicles. So net zero is awesome for many reasons, but it's very important to have efficiency first. Otherwise, we keep on consuming energy, and compensating via production of PVs becomes impossible once we start accounting for EV charging on site. Can all sites have 800 square feet of PVs installed? I don't think so. That becomes very difficult to do. So in order to keep on having this approach, then the building envelope needs to be dramatically more efficient, and we get there by switching to passive house. Now, embodied carbon, in the main report, we address embodied carbon and resource efficiency. Embodied carbon is not addressed by any of the standards that we covered. You can factor that in by the use of these tools, pH ribbon, as well as beam estimator, but none of the 12 building standards that we evaluated for this report actually addresses this. Something that is interesting that we describe pretty well in the report is the concept of resource efficiency. Just to give you an idea, we compared a performance-based standard PHI low energy building and a prescriptive standard Fuse 2021 core prescriptive, and we selected projects of those 50 where the energy performance of the two standards would fall within 20% of each other. We did that, and we found out that in average, I'm going to skip a little bit here. We found that in average, you could get to the same energy performance with the performance-based approach and avoid using, in average, 830 cubic feet of insulation, just because the support of the energy model tells you how much an R value or a solar heat gain coefficient does for your project. Whereas the prescriptive approach is blind to the actual performance. And what we found, we also benchmarked our fees for the modeling of these projects, and the performance-based approach, even including what we charge for those projects, was still about $5,000 cheaper than the prescriptive approach. So we found the prescriptive approach to be pretty wasteful in terms of resources. Don't really have time to go over that in detail, but you'll find that in the main report as well as on our YouTube channel. So conclusions, even in California, mild climate conditions, Title 24 failed to deliver comfort in half of the projects considered. For indoor air quality requirements, airflow, rate per occupant, filtration grade, air tightness, and mold prevention, PHI requirements outperform both Title 24 and Fuse. Title 24 addresses air filtration and does not address at all the air tightness of the building. So in my opinion, that is a job half done. For resiliency, Title 24 performs poorly as priority has been given to active systems such as heat pumps and PVs. For passive system, that is the building envelope, are close to and in some aspects underperform the 2018 IECC standard, for example, the air tightness requirements. The adoption of air source heat pumps shifts the priorities of improving the passive to improving the passive building performance in wintertime. The reduction of combined heating and cooling site energy, passive house outperforms all other building standards, 55% reduction compared to Title 24, with the 2018 Fuse Plus Core ranking second. And the adoption of performance-based passive building standards can significantly reduce the need to increase production of electricity when electric vehicles are more widely adopted. This is the summary. You can find the full report at this link, and as well as YouTube. We have individual videos. We have a California-specific CE unit coming online in Q1 of 2024. As Ken mentioned, in the fall of 24, we are going to be in California, and PHN has in January a cohort for the passive house designer and consultant training coming online. That being said, I look forward to the chat with Ken and to your questions.
Fantastic. Thank you, Enrico. That is a lot to take in.
Yep. 2.5
I'm
years
sure
of-
everybody's heads are spinning. It's really amazing work. It's really just a huge accomplishment. And of course, I think maybe talk a little bit at first, as much as there is in this report. We were talking the other day and you're like, oh, there's just so much more data. You could have like a series of reports. Like, what did you leave out, just as we're curious, and what was the selection process? I mean, you talked about what those key metrics were there, but
that's a great question. It took 2.5 years to get here. And during that time, something that I really value is having good questions, because we can find this is the age of information. We can find any answer that we want. But formulating a good question is something that takes time. And I value, that's why I like teaching, because I get so many questions that I learn a lot from them. I learned a lot in this process. In the main report, we talk about the breakdown of heat losses and how, if you Google or if you go on YouTube, you will find builders claiming that 50% of all losses are through air leakage or 40% or whatever. And that is far from being true. Both for the 2021 code and for passive house, air leakage counts for like 10% of the total heat losses, with windows and exterior walls being much higher than that. Losses to the ground, heat losses to the ground count more in terms of heat losses than air leakage. So that is something that I found very interesting, as well as parameters for indoor air quality, like the filtration grade for the MERV rating and the EPA indoor air plus. Parts that I have left out were due to having to put an end to this. Because if you think you're over this after 1 hour of presenting, I'm way past this. We are looking at, for example, thermal mass is something that PHI's research has very well indicated has not been as relevant or as much of a priority compared to windows, air leakage, and all of that. We want to develop that further in the modeling. I had to leave that behind because it's something that is more for the textbook and for warm climate CE units coming up than for the main report. There's a lot that we left out. Like, this is half the data. Yeah.
yeah, I mean, we were talking, I think, about ventilation efficiency.
Yeah.
The effects of that, and
yeah. Ventilation efficiency is a big one. Even I started for this study, I started developing an hourly energy modeling tool. Because at some point, this is something that on one side, ventilation, especially in cold climates, has frost protection, and that is often misregarded or disregarded. Or when we have heat pump water heaters that take the room heat to create domestic hot water, they steal the heat from the room, and the heating system has to make up for that. And another parameter. So that's something that I actually reached out to Jürgen Schneider at PHI. He was very kind and to listen to me. But that is a whole new step in looking at the exchange of energy between the building and the grid, because we are going to end up with a ton of PVs that produce electricity during the day, and then there's nothing at night. So for priorities, even for California, heating has to be a higher priority, because the most heating happens at night when there's no production from PVs, whereas cooling happens during the day, so you can have instant self-consumption of what you produce on site. So
right.
that is in the next level or next step in the actual carbon considerations for the exchange between the building and the grid. And all of this we left out.
Yeah.
Yeah.
No,
I,
it just goes on and on. So a couple of things based on what I'm seeing in the chat regarding heat pumps, a few different questions here.
Mhm,
Ground source not included
mhm.
compared to air source, correct?
Correct. This was
It's
all
just
air
air
source,
source.
yeah, air source out of cost. And we've had not that I disregard ground source. I'm likely going to have a ground source heat pump in my own project. It was just trying to focus on the important, that is the how the building protects people, and heat pumps only address energy efficiency. And we wanted to have something that would be fairly comparable from climate zone 2, Texas, to climate zone 7, Colorado. So from very cold climate to very hot climates. So it was one of the decisions we had, one of the lines we had to draw in developing this project.
Yeah. And sticking with heat pumps for a minute, in this whole idea of resiliency and investing, it was really interesting your comments about Title 24 versus Passive House in terms of the power going out and the focus being on heat pumps, and them no longer being useful. We like to say that, you know, we like technology in Passive House, but we want it to enhance high performance, not to compensate for poor performance. And coupled with that, so a couple of thoughts on that, and then also just the speak a little bit more about the idea of the heat pumps doing better in the cooling than in the heating, and how that exaggerates kind of like the difference and the importance of the enclosure and the resilience.
Yeah, 100%. The I forgot the first part of your question. I'm sorry.
It's just the focus on the heat pumps as the answer, as
Yes.
opposed to the resilience. And it wasn't so much a question as just looking to elaborate.
So when it comes to comparing apples to apples, which is very hard to do with so many building standards, we built all these energy models and made them to comply with different building standards. And when I was working on the California Title 24 envelope, I was surprised how close it is to the 2018 IECC. And so this comes back to the opinion or belief that there may be in the market that California Title 24 is so much better than national code. And with regards to the building envelope, I didn't see that. Like, for real, did not see that being better. And there are some jurisdictions, I have a couple in mind, where maybe they were greener or better in the 70s or 80s, and that fame stayed, and they have not kept up with the pace. So that is one consideration with regards to Title 24. If you look at U values or R values for windows, for your ceiling, your roof, they're very close to the ICC national standard. That is one big finding. Then looking at heat pumps, if you look at a data sheet for a heat pump, the two parameters that every builder and every actor and every engineer knows is HSPF, heating seasonal performance factor. So how efficient it is in the wintertime for heating, and the SEER or SEER2, seasonal energy efficiency ratio. So basically how efficient it is for cooling. And the SEER or SEER2 is always higher than the heating performance, typically 2 or more times better, meaning that for every unit of energy you give to that heat pump, it will produce twice as much cooling that it produces heating. So if you look at the heating demand, you divide it by the HSPF, you look at the cooling demand, you divide it by the SEER. In other words, the heat pump is much more efficient in producing cooling. So you're building the envelope, the bones have to be better for the heating part, because there's a factor of 2 or 2.5 that the heat pump favors the cooling, so the building has to be better for heating.
Great. Yeah. I mean, it's amazing to see the differences jump out there in the graphs.
Yeah, visuals sometimes make the difference, because looking at data sheet, you don't really care. But once you see it, like, dude, the blue is twice as big than the orange, literally. So that makes a big difference, especially in California.
Even in Southern California.
100%, absolutely.
If you had a magic wand and you were able to change one or two things in the California building code, um, what would your priority be?
Well, the air tightness needs to be addressed.
Yeah.
That is a job not done. I'm sorry. That is, I think everybody outside of California will agree with me about that. That is, to me, the biggest missing piece, because air tightness, air leakage, I mentioned, counts not as much as it is believed to do for the energy performance, but it does, as it does for the indoor air quality, as it does for comfort, as it does for noise control. So you get a lot of value out of that. And it's 2023, not having any requirements. It's 2023, it's time to do it.
Right. Absolutely. There was a question about like looking at, you had the 12 building performance standards, which included, and I don't remember if you mentioned it here, but the Pretty Good House
Mhm.
as well. There was a question about comparing it to like a LEED standard, a gold building or something, or
Yeah, I got the question before. We had to make choices, and LEED did not make the cut, nor did the Living Building Challenge, nor did other standards. Living Building Challenge, last time I checked, they were charging you to download the standard, and to me that is insane. For LEED, just did not look into that. We had to draw a line. I thought that 12 was enough.
certainly when you look at those graphs, you know, the spreadsheets, it's
Yeah. Well, it's a lot of numbers.
mesmerizing. Uh, Going back to code, there are a few comments and questions about the potential of like fixing the code with Passive House, just inserting Passive House in California or generally. What's your thought about Passive House being an alternate pathway or its viability as as a as a floor of performance rather than a ceiling?
So for that to be successful, it takes a significant shift in mind frame for thousands of people, and that takes time, in my opinion.
Yeah.
One of the biggest thing, and one of the main conclusions of the main report is that to get anywhere, reduction of carbon, embodied operational energy, all of that, we basically need to set goals and have performance-based approaches to meet that. And coming from Europe, there is no prescriptive approach in Europe, period. Zero. And to a fair amount, it is more free than having prescriptive approaches. When we do consulting, sometimes we get a ceiling that is not R49, and who cares? Because the whole building is a passive house. And so, but we get calls from builders so concerned, like, hey, the ceiling is missing an R5. Who cares?
Right.
And to me, that should be the goal, to have passive house as the code, but it takes time. That is one of the reasons why we switched to being education providers, because it's very hard to change people and change a muscle memory that is in place at any level. City inspection, builders, architect, all of it. To this day, we kept asking, "Oh, what is the R value that we need for passive hours?" Like, I need to model it. I don't know. That is not the metric. So that is, to me, like, if you are watching, if you're in a policy position, scratch prescriptive approach entirely, performance based. That is not to passive house yet necessarily, but a step code that is performance based, leading to that.
Right.
So go ahead.
Now, and another good, I'm happy to, I'll pre-announce here, I don't think PHI will mind too much, that coming in the new year, we're expecting in January even, a simplified calculation method in the PHPP, coming from design PH into the PHPP for single family homes, where it's massively simplified and expediting the design as well as the certification going forward. So we're excited about that, while still calculating and having it be a performance-based standard with the trade-offs and
Yeah,
optimization.
I'm excited about that myself. But you take the heat for leaking
Yeah.
it out.
I don't think they mentioned it was top secret.
No,
Although it was in a closed circle of conversation with the certifiers last week, right? Um, and I think it's important. I don't know if we talked about the fact that you're actually a building certifier as well.
oh yes.
One of the things that folks in coming to this, it's really interesting that there are over 30 certifiers outside of PHI that are working in building certification across the United States. And so Enrico, and is really flexing his muscles here today, is showing a level of institutional knowledge that everybody should be accessing. And the best way to access it, of course, is through certification, and going through the process. What else there was a comment in there about what if we did a smaller subset. So you did the California north to south,
Mhm.
smaller subset of Southern California, how you don't get the spread. What's your,
Well,
can you characterize it?
for data to be, so these are actual projects.
Yeah,
So there's ADUs, homes, larger homes, but these are actual projects, each with its own orientation, form factor, neighbors, trees, glazing. And so going less than 10, I would be very wary of the results being significant, because the peculiarities of each individual project will weigh in a lot, you know. So the only other state I would be comfortable doing it with is Colorado, because there is a dozen. We actually have a cajillion other projects. And so the number of projects needs to be high enough for the results to be statistically relevant, you know.
right. But
We have one project in New York State, and that is not, it is a project, but it is not, it does not drive the law for passive house in the state of New York, you know.
right. I guess the issue is, though, that everybody's focused on Southern California because nobody quite believes that it's significant enough, right? It feels like a magic trick. And but the data, like if you just took some of those those homes that you had in the graph,
Mhm.
and folks can go online and look at them and study them, uh, you know, they do show quite a dramatic
Well,
difference.
and the value is one of the reasons why we focus not just on energy, but on 5 metrics: comfort, indoor quality, durability, energy, and carbon, is because buildings right now there's a very high focus on embodied carbon, which is great. Uh, in this context, Southern California does not shine for performance for passive house in terms of energy, because the climate is so mild, but it's one of the most polluted areas in the world, you know. So the air tightness, filtration, and fresh air supply are super key and super valuable. When we work with owners that are working on their own home, that is super high in the energy is kind of like in the background. It's important, but that's like whatever. But indoor quality and comfort rank very high.
Yeah.
And Passive House does that very well, especially compared to Data 24.
Yeah, that's our experience I mean, I'm in New York, and acoustics as well ranks quite high. Having peace and quiet in your
Yeah,
home,
yeah, that
very
is
important.
100%. Yeah.
Well, this was terrific. Amazing presentation, amazing range of questions. Oh, I didn't want to avoid it. There was early on. So the question that I raised to you earlier in the week,
Mhm.
regarding the 1 bedroom plus 1 bedroom, I don't want to get sidetracked by it, but I do think it's important to just note, um, you know, whether the bedroom plus one is related to the internal heat gains, I believe, and
In this case, I only used it for the ventilation rates.
right,
In this study, that occupancy was only used for the, sorry, throughout the entire study, the occupancy was bedroom plus one. So actually 62.2.
right,
Only for the ventilation rates was, I called out the fuse one separately because in the guidebook of fuse, it calls out for that in determining the supply rate for the ventilation system.
right. So, but the supply rates were done based upon the same reference across the board.
No.
Is that what I misunderstood. Restate what you said. Sorry.
Yes. So for the for everything except for the ventilation rate, so interior gains and all of that,
Right.
bedroom plus one.
Yep.
Ventilation rates, Title 24 follows actually 62.2, so bedroom plus one. Fuse has its own at one bedroom equals one occupant, not plus one. And PHI, we actually use the airflow rates that we expect for the actual projects, which is a combination of occupancy, extraction, and volumetric.
Okay, good. Good. Great to just touch on that. Ever like to get into the weeds here. I guess the last thing before we go, maybe I just was really fascinating and eye-opening to see the graph where you put the EV cars and the Title 24 efficiency next to Passive House, and you almost get like a whole car for free.
Correct.
With Passive House.
Yeah, nationally that is 2 cars for free. California is milder, so every building needs less heating and cooling, but you still get basically 1 car for free with PHI Passive House.
And the rest of the country is 2 cars for free.
Correct. Yeah.
Nice.
Yeah, that is something that I found very fascinating from the results that I found, and that has become one of the narrative points of the energy, because the more EVs we have charging at home, the more that is going to change. And that is a way to relate the energy efficiency of a building to something that people can see and understand.
Right. It's like carrying a bundle of wood.
Yes.
The latest version.
Yes, the coolest version.
Fantastic. So why don't we leave it there? We'll declare victory for the day and say thank you so much, Enrico. I encourage everybody to go on. If you just Google YouTube and Emu and building standard, the videos will come up. I think Mariana also put them in the chat. Keep an eye out for the tradesperson courses next year, our CPHD course coming up in January. And yeah, we need everybody to dig in, to educate, to share. This peer-to-peer knowledge sharing is really the superpower of Passive House. I don't know, you were going to say something, Enrico.
Oh no, I was just about to thank you and PHN for having us.
Yeah, thank you for coming on. It's been a pleasure. I hope everybody has a good day, and I don't think this will be the last we hear of it. We look forward to digging in and using it in many ways going forward. Thank you, Enrico.
Thank you so much. Thank you.
Have a good day, everybody. Thank you for being with us.